In 1354, observers in Perugia, Italy, watched closely as the sun was rapidly swallowed by a black disk. The sudden, unexplained darkness cast an unnatural twilight over the city, leaving the people looking, as one historical record states, deathly pale. To early civilizations, the disappearing sun was a direct existential threat. In 2136 BC, Chinese citizens banged pots and made frantic noise, attempting to scare away the mythological dragon they believed was actively eating the sun. By 648 BC, the Greek poet Archilochus described a similar event by claiming the god Zeus had angrily turned midday into night. Humanity's first collective reaction to the cosmos was pure panic. They treated the mechanical sky as a canvas of unpredictable, angry gods. Eventually, early societies transitioned from screaming at the sky to systematically tracking it. By 444 BC, Chinese astronomers logged the earliest reliable report of stars and planets like Venus and Mercury becoming visible during the day. They recorded the exact time, duration, and magnitude, the specific fraction of the sun covered by the moon. A Babylonian tablet from 247 BC reveals that early astronomers were eventually able to predict an eclipse months in advance. By recording the exact timing of these omens, ancient civilizations inadvertently created humanity's first massive, long-term scientific dataset. Moving into the medieval era, eclipses proved powerful enough to actively halt human conflicts. In 1451, the Seneca and Mohawk tribes were preparing for battle when totality swept over their camps. Both sides immediately sued for peace. Observers also tracked biological impacts. Chinese records from 1275 and 1514 document intense animal panic. Scribes specifically noted domestic animals fleeing into the forest and ducks returning to their roosts in the middle of the day. Humans were no longer simply looking up in fear. They were looking around, treating the eclipse as a measurable biological and environmental event. During the Renaissance, observation shifted toward the actual physical mechanics in space. This animated diagram shows an annular eclipse. In 1567, Christoph Clavius noted the moon did not completely cover the sun, leaving a narrow ring of light. This ring of fire proved celestial bodies vary in their relative distances, scale, and orbits. With Clavius's work, the eclipse moved firmly into the realm of geometry, a physical event governed by the specific distances between three spheres. By the 19th century, new technology turned the brief moments of totality into a rare opportunity for high-precision physics. In 1851, a photographer named Berkowski captured this objective, permanent record of a totality in East Prussia, revealing the blackened sun and the glowing corona.
British astronomer Sir George Biddell Airy used the blocked sun to discover a jagged, reddish layer of the solar atmosphere. Because of its reddish color, Sir Joseph Norman Lockyer correctly identified and named this layer the chromosphere in 1868. Temporarily blocking the sun's overwhelming main light was the only way early astrophysicists could discover the complex, invisible structures burning around it. The most significant test of physical laws occurred in the early 20th century, during those few minutes when the sun's light was gone. The darkened sky of a solar eclipse provided the specific conditions Albert Einstein needed to prove his general theory of relativity in 1916. Today, astrophysicists are still heavily relying on the panicked ancient records from the beginning of our story. This map visualizes the Earth's rotational clock error, delta T, showing our planet slowing down over thousands of years. Because ancient scribes and monks recorded exactly where it went dark, scientists can calculate this exact rate of planetary deceleration. The record of the dark sun is a rare through line in history. The observations of ancient scribes provide the data modern physics needs to calculate the precise motion of our planet.